Hey everyone! Today I have a super quick but interesting topic for you. You've probably heard that hanging transactions are bad for database performance, but why exactly? Let's try to understand what's really going on behind the scenes. Imagine many transactions constantly interacting with the database. Over time, some transactions start, do their work, and successfully commit their changes. However, sometimes transactions run very heavy queries or have to wait to acquire a lock. In these cases, they remain in an active state for a while, effectively hanging in the system, like transaction 10 in our diagram. In PostgreSQL, every transaction has its own view of the database. At the beginning of each transaction, PostgreSQL creates a snapshot, not a physical copy of the data, but a set of numbers such as the IDs of active transactions. This snapshot determines which rows are visible to the current transaction. In our example, transaction 10 sees all the changes that were committed before it started, meaning the transaction IDs of those changes are less than 10. The same principle applies to all other transactions. But then the question is, why is a hanging transaction like transaction 10 actually a problem? In order to understand this, we first need to understand how updates work in PostgreSQL. Let's say we have a row with ID equal 1. Internally, PostgreSQL stores two special transaction IDs for every row. These are hidden system columns. xmin stores the ID of the transaction that inserted the row, and xmax stores the ID of the transaction that deleted the row. For example, if transaction 5 inserts the row, then xmin equals 5, and xmax is null because the row hasn't been deleted. Now here's the interesting part. When you update a row in PostgreSQL, it doesn't actually modify the existing row. Instead, PostgreSQL creates a new copy of the row with the new values and marks the old version as deleted. So if transaction 7 updates the row, PostgreSQL set xmax to 7 on the old version and inserts a new version of the row with xmin equals 7. If later transaction 11 updates the row again, the same thing happens. The current version gets its xmax set to 11, and a new version is inserted with xmin equal to 11. At this point, you might think that PostgreSQL could immediately remove the old versions using vacuum, but it's not that simple. To understand why, we need to take a closer look at transaction snapshots. Let's look at the timeline and see when each version of the row existed. Version 1 was inserted earlier, at this point in time by transaction 5. Later, transaction 7 updated the row. At that moment, version 1 was marked as deleted and version 2 became the current version. Then, transaction 11 updated the row again, version 2 was marked as deleted and version 3 was created. And version 3 is still the current version that exists now. We already know that when transaction starts, it creates a snapshot where all committed data is visible. For example, transaction 12 sees the version 3 of the row because the changes has already been committed. When transaction 10 started, the latest committed version of the row was version 2. Since version 2 was visible to transaction 10 and could potentially be used by it, PostgreSQL cannot remove it. As a result, the longer a transaction runs, the more old row versions must be kept, because they might still be visible to that transaction. This also means that vacuum cannot clean up those versions yet. The point in time where the oldest active transaction started is extremely important for PostgreSQL. This point is called the event horizon, and it defines the boundary before which deleted rows are guaranteed to be no longer visible to any active transaction. Because of that, vacuum can safely remove row versions that are older than this horizon, since no active transactions will ever need them. Hanging transactions hold back the event horizon, and this seriously degrades database performance. Because of them, vacuum cannot clean up the row versions. As a result, tables and indexes start to bloat and queries become slower over time. Long-running transactions can also cause replication issues and may lead to increased lock-in. The impact on performance can be dramatic. Database throughput can decrease very quickly. The number of transactions per second drops as the long-running transactions continue. In one experiment, I found the number of transactions per second became 6 times lower after just 15 minutes of a hanging transaction. So the effect is significant, and long-running transactions can severely harm database performance. That's it for today. I hope you learned something useful, and now you'll keep an eye on long-running transactions. Thank you for watching, and see you in the next video. Bye!